We're now moving on to 21.3, radioactive decay. Here we're going to recognize common modes of radioactive decay, identify common particles and energies involved in nuclear decay reactions, write and balance nuclear decay equations, calculate kinetic parameters for decay processes including half-life, and describe common radiometric dating techniques. So when you have a spontaneous change of an unstable nuclide into another, you have radioactive decay. That unstable nuclide is called the parent nuclide, and the resulting nuclide is called the daughter nuclide. It may be stable, or it can also undergo decay. So here's an example. Our parent nuclide here, uranium-238, and it is giving off an alpha particle, and that produces thorium-234 as the alpha particle removes 2 protons and 2 neutrons from the uranium-238 nucleus. So let's talk about the types of radioactive decay. And we classify it based on the radiation that is produced. So the first, alpha decay, is the emission of an alpha particle from the nucleus. So you have, and then the daughter nuclide ends up being closer to the band of stability from that chart we looked at in the last section. So one example would be polonium-210, giving off alpha particle and giving us lead-206. Beta decay is the emission of an electron from a nucleus. So the way this works is you have a neutron that is converted into a proton and a beta particle. So this is not an electron from this that are surrounding a nucleus. So not one of your shell electrons or any of that. It's actually coming from the nucleus itself, not from the surrounding electron shells. So that nucleus converts itself into a proton and a beta particle. And this happens when you have a nuclide that has a large neutron to proton ratio. And the mass number does not change, but the number of protons is increasing and the number of neutrons decreases. So this ends up overall lowering the neutron to proton ratio and bringing this daughter nuclide closer to the band of stability. An example here is iodine-131. Okay, there's our beta particle, and this decays to xenon-131. So the mass number is not changing, but that one neutron turned into a proton and an electron, so our atomic number goes up by 1, and our number of neutrons decreases by 1. So the mass number overall does not change, but our atomic number does. And then you can see now we have this higher atomic number, and since we have one more proton and one less neutron, we now have a lower neutron to proton ratio. The next type is gamma emission, and this occurs when a nuclide is formed in an excited state. Wow, that is not how you spell excited. Oh well. It should be a T. And then it decays to its ground state, emitting a gamma ray, which is a quantum of high energy electromagnetic radiation. So the mass number and atomic number do not change here unless there's some other type of radiation that's occurring simultaneously. One example is cobalt-60. And to show that it's an excited nuclide, we put a little asterisk, and then we show giving off the gamma ray, and we still have the same mass number and atomic number, but again we gave off that gamma particle. So lots of energy coming off there. The next type is positron emission, or beta plus decay, and this is the emission of a positron from the nucleus. And this is observed when you have a low neutron to proton ratio and your nuclides themselves are below the band of stability. So what happens is you have a proton that is converted into a neutron and a positron is emitted, increasing our neutron to proton ratio and bringing the daughter nuclide closer to the band of stability. An example of this is oxygen 15. Okay, so there's our positron and making nitrogen 15. And then we have electron capture, and this occurs when an inner electron in an atom, so one of the electrons that's like closer to your nucleus, that's orbiting your nucleus, is captured by the nucleus. So it ends up combining with a proton and converting into a neutron. But now you have this inner shell that has a vacant spot for an electron. So one of your outer shell electrons comes down and fills that inner vacancy, emitting energy in the form of light. Usually it's an X-ray. This tends to occur for nuclei below the band of stability, and it decreases your atomic number by 1 and does not change your mass number. So this is increasing your neutron to proton ratio. And you end up with a daughter nuclide closer to the band of stability. One of the way that this is determined whether something goes through positron or electron emission or capture has to do to kinetic factors. Whatever one between those two has the smaller activation energy is more likely to occur. So they both are kind of similar in that they are observed at a low N to P ratio and they're below the band of stability. So it really just depends on kinetics which one, whether it's positron emission or electron capture, will occur. And an example of electron capture, we have krypton 40. I'm sorry, not krypton, potassium. Okay, and so there it is grabbing the electron to give us argon 40. So you see that mass number does not change, but the atomic number goes down by 1. So this is just kind of an example of how we can determine the type of radiation coming off of something that's radioactive. Alpha particles are attracted to a negatively charged plate and slightly deflected. So because that they have to be positively charged and large because of this. Beta particles are attracted to the positive plate and deflected a bit, meaning they have to be negative charged and relatively light, but they have some mass. And then gamma rays aren't affected by an electric field at all, and they just go right through, so they are uncharged. And your book gives you a very nice table summarizing the different types of our decays and their nuclear equations and what changes. So I would definitely mark this page in your book, or whether it's online, which OpenStax lets you do bookmarks, or you have physical book, whatever it is, I would definitely mark this to be able to refer back to it. Positron emission tomography or PET scans are use radiation to diagnose and track health conditions and monitor how treatments are affecting a patient's body. So a positron emitting radioscope is produced in a cyclotron and then attached to a substance that is used by the part of the body being investigated. So it's tagged with what is called a radio tracer and then put into the patient, usually either an IV or it's breathed in as a gas, and to make the different areas of the body light up so they can look at it. These are very commonly used to observe cancer, tumors, and to monitor treatment. So now let's talk about radioactive decay series. So the naturally occurring radioactive isotopes of the heaviest elements actually fall into chains of successive decays, and all the species in one chain constitute what is called a radioactive decay series. For example, we have the uranium series, actinide series, and thorium series. These are 3 of the most common. There's also the Neptunium series, but it's really not significant because everything has really short half-lives. Every series has a parent that has a long half-life and then a series of daughter nuclides. And what's interesting about these three in particular is all of them have an isotope of lead as their stable end product. These are all on the band of stability, and yeah, they all end at an isotope of lead. So here's the uranium-238 radioactive decay series. So it's got 14 different steps with 8 alpha decays and 6 beta decays until eventually it ends at lead-206. So you can see, okay, decay, 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 and then we chill out once we hit lead, which is on the band of stability. So now let's talk some kinetics, because radioactive decay follows first order kinetics. So a lot of times you hear the term half-life being referred to for radioactive materials. Every nuclide has a characteristic half-life, and these can vary across all different radioactive elements. Some of them might have a half-life of a couple minutes or a couple hours or seconds, while others might have one of billions of years. So you can't just go, oh, it's radioactive, so its half-life should be like 30 years. Nope, it varies greatly. So the half-life is the time required for half of the atoms in a sample to decay. If you remember from kinetics from the beginning of this semester, the half-life of a compound in a reaction is equal to the natural log of 2 over K, the constant for first order, which can be simplified to 0.693 over K. But when we're doing radioactive decay, instead of using K, we use lambda as our decay constant. So now we say T1/2 equals natural log of 2 over lambda, or 0.693 over lambda. When it comes to the first order equations that are relating the amounts, instead of using A to represent concentration, we use N for the number of nuclei. So instead of saying AT equals A naught e to the negative KT, it's NT equals N naught e to the negative lambda T, or T equals 1 over lambda times the natural log of NT over N0. And here's just showing you some first order decay of cobalt-60. Has a half-life of 5.27 years. So that means after 5.27 years, 50% of it remains. And then after another 5.27 years, now that 50% is divided in half, so now 25% remains. And that's 2 half-lives. Then after a third half-life, now we're at 12.5%. So after every 5.27 years, half of whatever you have is gone. So we're going to look at an example. Cobalt-60 decays with a half-life of 5.27 years to produce nickel-60. And we want to know the decay constant, the fraction of the sample that will remain after 15 years, and how long it takes to disintegrate to only 2% remaining. So let's start with A. We want to figure out the rate constant, and we know from our kinetics that T1/2 is equal to natural log of 2 over lambda. Or 0.693 over lambda, and we're looking for lambda. So lambda is equal to 0.693 over our half-life. So that's 0.693 divided by 5.27 years. And so that gives us 0.132 inverse years. For B, we want to calculate the fraction of cobalt-60 that will remain after 15 years. So this fraction that is left after our time is, we're looking at NT over N0. That's what we're solving for here. So we can use N0 or N naught is equal to, or I'm sorry, not N naught, NT is equal to N naught times e to the negative lambda times t. So then NT divided by N naught is equal to e to the negative lambda t. So that equals e to the negative 0.132 years times our time here. It wanted 15 years. Oops. Sorry, this should be inverse years for negative 0.132, and we can see years cancel. And that gives us 0.138 for our ratio of our amount to our starting amount. We could also say that there's 13.8% remaining. And then for C, 2% of the original amount. So 2% of what we started with, we could say is the same as it was 0.0200 times n0. So we just change it to a decimal. And we also know that our time is equal to negative 1 over lambda times the natural log of nt over n0. So this is negative 1 over 0.132 inverse years times the natural log of 0.0200 n naught over n naught. Because remember, we don't actually know what n naught is, but when we do this, we see it divides out because we're just looking at a fraction of it. And so then this becomes 29.6 years. Okay, so radiometric dating. This uses the half-lives of radioisotopes to date the origin of artifacts, fossils, geological formations, etc. The most common that most of us have heard of is radiocarbon dating or carbon-14 dating. And this is for carbon-containing substances, very accurate up to 30,000 years old, reasonably accurate around 50,000 years old. So what's happening is carbon-14, which does naturally occur but in a very, very small amount, decays by beta emission and has a half-life of 5,730 years. And so what we do is we can look at the change in the ratio of carbon-14 to carbon-12, as this ratio is constant in a living organism. But when it dies, this is going to decrease over time because now this carbon-14 is decaying and not staying constant in the organism. And then we can look at how that ratio changes and kind of back calculate then how long it's been or how many half-lives that it has gone through. Now this only works for about 10 half-lives. So this again has this upper limit around 57,000 years. After that it starts becoming less and less accurate. There are other radioactive nuclides that are used to date older events. For instance, for rocks, a lot of times uranium-238 is used because it has a half-life of 4.5 billion years for it to decay to lead-206. Potassium-40 decays by positron emission and electron capture to argon-40 with a half-life of 1.25 billion years. And rubidium-87 decays to strontium-87 with a half-life of 48.8 billion years. So this is a little picture kind of showing what's happening for radiocarbon dating. Carbon-14 is taken in by plants and animals when we breathe, giving us this constant level. So this is plants and animals. But after death, that carbon-14 is going to decay, so the amount of carbon-14 relative to the amount of carbon-12 is going to decrease. And so then we can compare this to how much is normal in a living organism to determine how long ago that organism lived and died. So we'll look at an example. A tiny piece of paper produced from formerly living plant matter taken from the Dead Sea Scrolls has an activity of 10.8 disintegrations per minute per gram of carbon. If the initial carbon-14 activity was 13.6 disintegrations per minute per gram of carbon, estimate the age of the Dead Sea Scrolls. So the rate of decay is going to be proportional to the amount of radioactive C14 left on the paper. So we know that we have that T is equal to negative 1 over lambda times the natural log of NT over N naught. And we're going to go ahead and transform this to say that t is equal to -1 over lambda times the natural log of the rate of t at time t divided by the rate at time 0. I don't like using capital R's. I like doing lowercase r's for rates. I know I'm weird, but okay. So 0 represents when the plants were still alive or when they were cut to make the paper. Because when you cut the plant now, you've killed it, right? And then the t represents what the current time. So we can go ahead and figure out our decay constant. Carbon-14 has a half-life of 5,730 years. So then our lambda is equal to the natural log of 2 over 5,730, and this is equal to 1.21 times 10 to the -4th inverse years. So now we can go ahead and plug that into our equation as well as our two rates. So now t is going to equal -1 over 1.21 times 10 to the -4th inverse years times the natural log of our rate at our time t is 10.8 disintegrations per minute per gram of carbon. And that is divided by our initial rate, which is 13.6 disintegrations per minute per gram of carbon. So all those units cancel out. And then this comes out to be 1,910 years, approximately 1,900 years old. And so here's a picture of some of the Dead Sea Scrolls. All right, one more example. An igneous rock contains 9.58 times 10 to the 5th grams of uranium-238 and 2.51 times 10 to the -5th grams of lead-206 and much, much, much smaller amounts of lead-208. Determine the approximate time at which the rock formed. So very, very little lead-208, which is the most common isotope of lead. So we're going to assume that all the lead-206 came from the uranium-238. So when the rock formed, it had all of the uranium-238 that currently in it, plus the uranium-238 that underwent decay. So the amount of uranium-238 currently, is going to equal this 9.58 times 10 to the -5th grams of uranium, and we're going to go ahead and make this into moles, times 1 mole of uranium per its molar mass of 238 grams. So this is 4.03 times 10 to the -7th moles of uranium. And when 1 mole of it decays, we get 1 mole of lead-206. So then the amount of uranium-238 that decayed is going to equal 2.51 times 10 to the -5th grams from the lead-206. And we have 1 mole of lead for every 206 grams of it. And 1 mole of uranium for every 1 mole of lead. So this is 1.22 times 10 to the -7th moles of uranium. So the total amount of uranium-238 is equal to those two summed up. So that's 5.25 times 10 to the -7th moles. So now we can use our T equals -1 over lambda natural log of nt over n naught to figure out our amount of time. And then to find our decay constant, we can our half-life is equal to 4.5 times 10 to the 9th years. And that was given to us earlier, 4.5 billion years. So that's something that is given to us, that was given to us in our book when we were talking about the different types of decay. So it's not something you have to like figure out. So then our lambda is equal to the natural log of 2 divided by 4.5 times 10 to the 9th years. And this gives us 1.54 times 10 to the negative 10th inverse years. So we can plug all this now into our t. So that equals -1 over 1.54 times 10 to the negative 10th inverse years times the natural log of 4.03 times 10 to the negative 7th moles of uranium. So that's how much we currently have, divided by the amount we started with, which is that 5.25 times 10 to the negative 7th moles of uranium. And this gives us 1.7 times 10 to the 9th years. So 1.7 billion years old. That's an old rock.